So, good morning everyone. Today we will start with the last chapter, joint time frequency analysis. So, I'll be skipping some part of it due to the shortage of time. However, I will be discussing about some of the recent techniques which are being used in medical signal processing for the analysis of the signals. Okay. So, if you see the references, I have drawn from the time frequency toolbox by Augur, conceptual wavelets in digital signal processing by D. Lee Fugel, and lastly the level manual by the National Instruments. Okay, so we have discussed about various types of signals, and we have discussed that there are signals, say for example, the sinusoids and all these things, which do not change frequency over a period of time, and these type of signals they are regarded as stationary signals. Now, if there are any signals which changes its frequency components over a period of time, then they are regarded as non-stationary signals. Say for example, the EMG signals. Suppose you are holding something or you are not holding something, so you will be getting a basal EMG signal with some frequency components. However, if you put some weight, our muscles they start to activate, and there is a change in the signal characteristics of the acquired EMG signals. Okay, so these kind of signals, all the biological signals, in fact, if you consider the ECG signal, which we consider it as a periodic signal, it is also not periodic. Say for example, you are sitting now, your basal heart rate is different. If you start running, your heart rate will increase. Okay, if someone is having some pathophysiological condition, say for the example atrial flutter or atrial fibrillation, the frequency changes. So these kind of signals where there is a possibility that the frequency characteristics will be changed over a period of time, they are regarded as the non-stationary signals, and it is these signals, these non-stationary signals, which cannot be efficiently analyzed using the Fourier series or the Fourier transform method. Okay, the reason being, when the atrial flutter will happen, when the atrial fibrillation will happen, you don't know. You need to have the information about the time at which that frequency component is arising, and this is giving rise to a new type of analysis, the recent type of analysis which are regarded as joint time frequency analysis. Okay, so in our conventional Fourier series and the Fourier transform, you will find we are having signal, say amplitude versus this thing, so we call it xt. Okay, so we have some signal like this. If you perform the transform, Fourier transform, then we get frequency, say omega, and amplitude. Okay, so we get some peaks like this. So what is happening over here? If you see, if you consider the first case, your frequency is missing. If you consider the second case, your time period is missing, the time information is missing. So the joint time frequency analysis signal processing techniques, they allow to analyze the signal components or the signal characteristics, that is the amplitude, time and frequency, all at the same time. Okay, so I hope all of you know that a signal can only be described when you are having all three of these characteristics. Say for example, you want to have this ECG signal, or say per se you want to find out the temperature variation. So you will be having amplitude, you will be having time, you will be having frequency component. So any signal, they are defined by a combination of all these three characteristics. Okay, so our conventional Fourier series and the Fourier transform method, no doubt they are very strong methods. However, they lack that in the time domain we will not get the frequency information, in the frequency domain we will not get the time information. Okay, so hence there is a need for some advanced kind of techniques which can allow us in getting all these three information in a single plane. Okay, so this is the idea. So any Fourier spectrum, as I told you, suppose you are having a signal which is having a 20 hertz component, then if you perform the Fourier transform, at 20 hertz you will be getting a peak. Okay, so how it is doing? So you are having the signal, say over here. So what it does, you are having it is being decomposed into several sinusoids. Okay, so what it basically does, if you basically see over here, if you have the signal components, it will start with an with a frequency which is having a very high frequency, say for example infinity, infinity. Okay, so it will correlate with the original signal. We will be finding out the correlation factor. Okay, if we will be after finding out the correlation factor, we will be getting the correlation factor, then we will be lowering the frequency component, we will be again doing it. So in this case, if you see, the first was the 40 hertz, second one was the 20 hertz, and last one is the 10 hertz. Okay, so when you are doing this kind of correlation factor, so this signal component, it will be showing a highest correlation factor with that of the 20 hertz signals, and hence at 20 hertz you will be getting a large peak. Okay, now we know that any signals can be broken down into various what you call frequency components. So it is a 100 hertz square wave. So if you perform the FFT, you get at 100 hertz one peak, and then there will be harmonics. Okay, so once you try to filter out these signal components by applying the filter, band pass filter, you see we get sinusoidal signals. Okay. Now similarly, if you are starting with ECG signals, this should not be uniform white noise, only the ECG signal, and if you perform the FFT, you will be getting something like this. And then if you start segregating the frequency components, we will be finding that even the ECG signals, which are non-stationary in nature, they are also modeled using the sinusoidal signals. Okay. So then the question arises, suppose we are having two types of signals which are having same frequency component. If you see over here, sharp and the inverse sharp, they are having same frequency components. Okay. Now, if you look into the nature of the curve is totally different. Okay. Now, if you look into the Fourier transform of both sharp and the inverse sharp, they are similar. Okay. So, since the Fourier transform says that you are having xt, from there you are going to the frequency domain, and from there you are again coming back. But in both sharp and the inverse sharp signals, you are having the same frequency component. So from the Fourier transform, whether you will be going, suppose this one, if you are getting this Fourier transform, so say you go to this one or you go to this one. So there is a fallacy in the Fourier transform. Okay, and hence there is a need for this type of joint time frequency analysis. Okay, so the first simplest method to do or to gain entry into the what you call joint time frequency analysis is the short time Fourier transform. Okay, what it says? It says that suppose you are having a signal like this. So what we should do? We will fix a window in the time domain. Okay. Suppose we take a 10-second window. Say for example, it may be smaller, it may be larger depending upon your requirement. So I take this signal component, I perform the Fourier transform. Then I shift this window to the next level. Again there would be a 10-second window. Then again we will perform the Fourier transform. Okay. Now in this way you can try to localize the frequency components and try to analyze what is happening with the signal. Okay. So if you look into the spectrogram of sharp and inverse sharp, so what we are getting? We are getting in the sharp, as our time is increasing, our frequency component is also increasing. In the inversion, it is decreasing. Okay. Now, in both the cases, you will see at lower frequency ranges, there are some distortions. Why this distortion is happening? Okay. Now, why this distortion happens is because when you have fixed this window, so what you have done, when you have fixed this window, there is a limit. So it will, if you try to find out the frequency, it will be able to, there will be a case where you will be having a sinusoid which completely fits in this window, and that would be your critical frequency. Okay, that would be your critical frequency of the window. If if your frequency is higher than that critical frequency, during the analysis you will be having at least one period within that window for the analysis. Okay. However, if the frequency is smaller than that window, not a complete cycle is there within that window period. So what does that do? That induces aliasing into your analysis. Okay, because the window is not capable to analyze a frequency component, and due to that reason, in STFT at lower frequencies you will be getting some distortions. Okay. So localization of the signals. So how you are localizing, you are having the time period, then within a particular time you are trying to localize. Then again there will be some frequency this thing. So within that frequency the range there will be some spread. Okay. So those are regarded as localization of the signal. So you will be getting some average time, you will be getting some average frequency. However, there will be some time spreading and the frequency spreading. And what are these? We will be discussing a bit later. So there is a Heisenberg-Gabor inequality which says the time bandwidth product should be greater than equal to 1. So why STFT is having problem in the lower frequency? Because of this inequality. If your time bandwidth product is not greater than equal to 1, you will be getting the distortions. Okay. So before this STFT came into existence and all these things, there was a concept called instantaneous frequency and group delay. Okay, so let us first talk about the instantaneous frequency. As the name suggests, at a particular instance, what is the frequency we wanted to find out. Okay, now for getting the instantaneous frequency, not only instantaneous frequency, even the some of the strong tools of the joint time frequency analysis, we have to convert the signals to the analytic signals, and then we can apply those advanced tools. Okay. Now, what are analytic signals? Analytic signals are nothing but xt plus of j Hilbert transform of xt. I'm not going into the details. So what does this do is that, suppose if you are having a signal xt, okay, the analytic signals, they will be having frequency components less than 0, their amplitude values will be put to 0. When we talked about any signals, we talked about that they are composed of frequencies starting from minus infinity to plus infinity. Okay, but what happens is that analytic signals are the signals where the frequency is less than zeros, they are completely shut down to 0. Okay, why? We will be coming to that a bit later. So this is the using these analytic signals we get this instantaneous amplitude and instantaneous frequency. Okay, so if you see the graph again, sharp and inverse sharp. So if you have the time and the mean instantaneous frequency, you get this kind of stuff. So from here you can say as the time is increasing, your frequency is increasing, and also in the same second case, as the time is increasing, your frequency is decreasing, and which matches with the their original curves or waveforms, right? Now, similar to the instantaneous frequency, we have group delay, which is corresponding to the time period which is related with the instantaneous frequency. Okay, and this is the equation. So, does instantaneous frequency and group delay, they define the two different curves in the time frequency plane or the same thing? So, if you see the waveforms, and if you see compare the MIF and GD, they appear to be same. Okay. However, there is a problem. If you see the frequency over here, it goes to 0 to 250. Over here also 0 to 250. The problem arises when your frequency component is reduced. Okay. So in the when there is a reduction in the frequency component, if you see the MIF, mean instantaneous frequency, and the group delay, both of the curves, they are not representing the same thing. In the previous case it was the same thing, however over here it is not the same thing. Why it is happening? It is happening because of the Heisenberg inequality. Yeah, Heisenberg-Gaber inequality principle. Okay, so now you understand what is the necessity of the time bandwidth product. Okay, so this was the disadvantage of this mean instantaneous frequency and the group delay fraction, where the time bandwidth product, it was playing an important role. So the question is there any need for other tools for characterizing signals in the time frequency domain? Definitely yes. Suppose if you are analyzing some signal, say ECG signal, and if you are trying to analyze at a later stage, you want to analyze say EEG signal over there. If your performance of the circuit it changes, or the performance of the algorithm changes, you would not like that, right? So yes, definitely we need that there should be some other advanced joint time frequency analysis techniques. So from here we get into the joint time frequency analysis. So first one is first class of solutions, the atomic decomposition, where we have the STFT, time scale analysis, and the wavelet analysis. So today I will mainly be discussing about the STFT and the wavelet analysis. Okay, and there is another second class of solutions, the energy distributions, which are regarded as the Wigner-Villay distributions, pseudo-Wigner-Villay distributions, and Cohen's class distribution. Okay. So these are the feature space of the Shannon transform, Fourier transform, Gabbard transforms, and wavelets. Okay. Now in the Fourier transform, what we have, if you see, this is the time axis, this is the time axis. So when we perform the Fourier transform, we basically take the whole of the signal, and hence if you see the window, it is very long. In Shannon, you must have heard of Shannon entropy. Entropy, it is quite often associated with the energy or the frequency. Okay. Now in the Shannon case, if you see, the frequency is being taken as the, in the frequency domain we take the whole window, and whatever the frequencies are there we take it. In Gabber, what we do, we have these windows, but these windows, they are what do you call, they are segregating both the time domain and the frequency domain. Okay, both the time domain and the frequency domain. On the other hand, we also have this Wavelet transform. We also have the this Wavelet transform. In this, if you see, this is time and this is frequency. Frequency is increasing. Now, when there is an increase in the frequency, if you see at the lower frequency, we are using a larger window. As we are going towards the higher frequency, we are reducing the window. Similarly, again, when we go up, we are again reducing the window, and it continues. Okay. So the advantage of the Wavelet transform is that it is a more robust kind of system or you can say क्या हुआ, क्या सोच रहे हो, nothing, कुछ तो सोच रहे हो. Okay, so what happens, depending upon the frequency component of the signals, if you need a larger window, you will be made available with the larger window, and for the analysis of the higher frequencies, if you need a shorter window, you will be having a shorter window for the analysis. Okay, and this is the advantage of the wavelet transform, and this is why you will find that in the current day you will most of you must have heard about the wavelet transform. Okay, so STFT, again, if you remove this portion, what is this? It is a Fourier transform. So what it is doing, this XU is basically a time fraction. Okay, what we are doing, we are introducing a window within the signals. Okay, so why we are introducing this window, we are cutting that window, and after cutting that window we are doing the Fourier transform of with that signal fragment. Okay, so if you go for this STFT of the word Gabor, if you find, so if you see at this location you should have got a mean frequency or mean amplitude, however, or mean time period. However, if you see, there is a spread in the time domain and there is a spread in the frequency domain. This is what is your time spread and the frequency spread, and the mean point, it is called the mean time or the average time or the average frequency. Now you understand what is mean time and mean frequency, time spread and frequency spread. Okay, so what it does, if you now see in this region, you are having several frequency component. Now by applying the Fourier transform, we have been able to locate these things. Okay, which was impossible in the case of Fourier transform. So Heisenberg-Gaber inequality. So if you use an impulse, what you call window, then you will be losing the frequency resolution, and if you apply an impulse window in the frequency domain, then you will be losing the time resolution. Okay. Now again, if you see the STFT spectrogram of a Hopper signal within this one, so this is the idealistic spectrogram, and this is your in general spectrogram. If you see, if we are using a window length of 128, uh, so there is a somewhat spread. If you see it, if you see over here, there should be a sharp transition, but herein there is no sharp transition. There are some overlaps over here. Okay. Now, if you reduce this thing, the window length in the time domain, okay, your frequency in this thing spreading, if you see, it is increasing. Now, if you for increase the time this thing, your frequency spreading is reducing, but the overlap in the time domain, if you see, it is much higher. Okay, so this is what your time spreading and frequency spreading can do with your analysis. Okay, and hence choosing the window size is of utmost importance for the STFT transform. Okay, now again some examples are there, so I'm not going into this. ECG signals, and again you are having the STFT spectrogram for that one. Then STFT denoising is there. I'm skipping this one. Then Wigner village. Okay, what it does is that I'm just telling you in short what it is doing. It is doing autocorrelation. Okay, autocorrelation of this one, and then it is trying to find out the frequency spectrum. Okay, now the problem, since it is doing autocorrelation, there would be, if there are two frequency components, say x and y, so you will be having something for x, you will be having something y, and you will be having some correlated functions. Okay, now these correlated functions, if you see, there are two atoms, atom 1 and atom 2. This correlated fraction, it appears as a noise. Okay, it appears as a noise. So these are called the interferences. And if these frequency components, they are located far from each other, this correlation fraction, if you see, as these atoms, frequency atoms, they are being spread apart from each other, these interferences, they are being subsided. Now if there are four Gaussian atoms, you can see the problem with the Wigner-Villay distribution. You will be having a lot of interferences. Okay, now coming to the pseudo Wigner-Villay. So in the pseudo Wigner-Villay distribution, what you have, h of tau, again a window in the time domain. We are introducing a window in the time domain. Now when we have introduced the window in the time domain, if you see the interference domains in the time fraction, they have been removed. Okay, however in the frequency domain, the interaction, it has been enhanced. It has been enhanced. So the problem with this analytic, if you do not use the analytic signals, is that you will get a large number of, yeah, problems. Okay, so this is why we need to use the um, signals which are analytic signals. So you see, when the analytic signal is not considered. Okay, so inbuilt, when you are using these MATLAB functions and other Python functions for the Wigner-Villay or the pseudo Wigner-Villay distributions, at the background they are converting the signal into the analytic signals. Then coming to the Wavelet transform, so we have already discussed in one of our previous classes, but still I will be discussing in short. As I told you, wavelet transforms, they are basically useful when the signals can change over time, and they are called the non-stationary signals. So what is a wavelet? The wavelet is a waveform of limited time duration that has an average value of 0. Okay. So suppose this is a cosine wave, and then we are having a dB0 wavelet. So in Fourier transform, the cosine waves or the sinusoidal waves, they are the basis function. In the wavelet transform, wavelets, they are the basis functions. Okay, and as I told you, the definition over here is that wavelet waveform is limited, is of limited duration, and it is having an average value of 0. Okay, so if you see, wavelets, they are limited within time, and if you find out the average amplitude, they will be having a value of 0. Again, I told you we change the frequency of the sinusoids in the Fourier transform by stretching it. Hearing, what we do, we stretch the wavelets and do the correlation. Okay, find out the correlation. Okay, now again, in that way we do it. And again, if you see over here, in the wavelet transform, in the 3D form, what we have the scale, which is basically the inverse of the frequency. So that's why you will see the larger area band, it has gone to the top. Okay, in our previous case it was in the bottom, because our we plotted the frequency, and due to this reason, this scale of what, scaling of the wavelet. So due to this reason, the plot associated with the wavelet transform, it is regarded as scaleogram. Okay, because we are scaling and doing the thing. And in the STFT, we call it spectrogram, because we are dealing with the Fourier transform, which usually deals with the spectrum or the frequency bands. Okay, here we deal with the scales. Okay, now again, that same thing which has been made to understood. So wavelet transform representation, it is being done in the scaleogram form, scaling of the frequency, or more precisely pseudo frequency of the wavelet. The term dilation, it is also used to describe either the stretching or shrinking the wavelet in time. So these are some of the common wavelets which are there. So among this, for the analysis of the ECG signals, Dobeshe series wavelets, they are usually used, and mainly dB4 wavelet. In short, we got Dobeshes, they are represented as dB. So dB4 wavelets are usually used for the analysis of the ECG signals. Okay. Then before coming to the continuous time wavelet, I would like to make you understand what are discrete time wavelets. Okay, so in the discrete time we have a high pass filter and a low pass filter. So the signal is being broken down into the high pass and the low pass filter, and again we will be having two reconstruction filters. One is the high pass reconstruction filter and the other is the low pass reconstruction filter. And when we add both these signals, we get the original signal S dash, which is similar to the this thing. Okay, so the low pass frequency component, they are regarded as the approximate coefficient, and the high frequency components, they are regarded as the detailed coefficients. And if you combine this H and H dash, then it is called high pass half band filter. And if you combine this L and L dash filters, then they are regarded as the low pass half band filter. Okay, this is what it has been shown over here. So what basically happens? So in the first level of decomposition, suppose this is your FM. Okay, this is your FM. So this will be FM by 2. Okay, then in the next level, what happens? This A1, it will be broken down into 2. Okay, and in this way it will go. And if you see, it is given UDWT. What do you mean by U? U means undecimated. Undecimated. Say for example, when we say undecimated, undecimation means, we have previously discussed that decimation means, suppose we are having a signal, say xt or xn equals to same 1, 5, 7, 8, 9, something like this. When we talk about decimation, we will be stacking off every alternate numbers. So we are reducing the size of the signal. Okay. Undecimated means when we are applying the filtering, then we are not stacking off the amplitude values. Okay. Are you getting my point? However, let us first discuss then. In the second case, when we get over here, see again in the second stage, we are breaking it down into A2 and D2. A1 has been broken down into A1 and D2. Now the question arises, what should be the length of A2? What should be the length of D2? What should be the length of D1? Since this is undecimated discrete wavelet transform, this signals, they will be of same length. Suppose if your signal, it is having a length of 100, all these things, they will be having a length of 100. A2 will be having a length of 100, D2 it will be having a length of 100, D1 it will be having a length of 100. Because what we are doing, we are breaking the signal, but we are breaking the signal in the frequency domain. We are not breaking the signal in the time domain. So frequency domain when we are breaking, we are basically band limiting the signal. We are not time limiting the signal. Okay. Now, even if you had considered A1, it would have been 100. Okay, it would have been having a length of 100. Okay, now if it would have been your decimated one, then what? Original signal length was S. So D1, it would have a signal length of 50. A1, it would have a signal length of 50. Now again, when you are breaking it down, again you are having two components. The length of A2 would have been 25, the D2 it would have been 25. Okay. Now this is again another thing. So the second level of decomposition and their reconstruction thing. Now you have understood that we are having a low pass filter, we are having a high pass filter. Again we are breaking it down. So what happens in the continuous time domain? In the continuous time domain, we start with a very small bandwidth width of low pass filter and very high bandwidth of high pass filter. Okay. Now, if you do this, now you can imagine that this kind of structure, it will be very long. Okay. Here we are having some discrete values. Over here, if you see Fm, Fm by 2. Okay, this should have been Fm by 4. That means this bandwidth is Fm by 4. So we are going at a discrete level. When we are talking about a continuous wavelet transform, these things, they are infinitesimally small. One is infinitesimally small, another is very large. Okay, so when you go like that, the transform what you get, it is a wavelet transform, continuous wavelet transform. Okay, now the problem with this kind of discrete wavelet transform is that suppose you are having a signal, say for example ECG signal, and it is having a bandwidth of 100. Okay, now in the first half you will be having the low one, 0 to 50 hertz. This one will be having 50 to 100 hertz. Okay. In the next level, 0 to 25, this would be having 0 to yes, 25 to 50. Okay. If there would have been another level, this level, it would have been broken into say 12.5 to 25 and say 0 to 12.5. Now if you see what we are doing, we are rejecting a large amount of number of frequency components. Okay, if there would have been a possibility that if you fine tune these things, say for example your ECG signal is corrupted with 60 Hz noise, power line interference. Okay, so for removing the 60 Hz power line interference, you had to remove the frequency component from 50 to 100 altogether. That means you are removing a considerable amount of frequency component from your ECG signals. That is not desirable. So the fun is that if we can even break down the higher frequency components, the detail coefficients, then there might be a possibility. So that possibility has been introduced in through the wavelet packet decomposition. So this is the root, means the original signal. Say you are having 0 to 100. So you are having approximate. This is the detail. Okay. So again, this is this is AA approximate. Of the approximate, this would be AD. Detail of the approximate first stage. Again over here, if you see DA DD. Okay. Similarly, this would be AAA, AD, ADA, or ADD. Similarly, DAA, DAD, DDA, or DDD. Okay. So even the detail coefficients, they are being broken down. So by doing this, we are increasing what happens over here. Yeah, the high frequency components, if you see, we are again breaking that down. Okay, and this 0 and 1, there again another representation. So 0 0, see A is 0 0, A is represented with 0 and D is represented with 1. So in textbooks you will find either A, and AD and all these things. In some books it may be represented with 0 and 1. It all depends upon you which what do you call this formula you want to use or notations you want to use. Okay. So now if you want to see 0 to 100, so we are having 0 to 50, 50 to 100. Okay. Now 50 to 75, 75 to 100. Now we know that 60 hertz is within this region. We can again break it down, say 62.5, again 62.5 to 75. So it is within this region. So we can again start breaking it down. In the previous case, what was happening? We were eliminating all this frequency component. So this wavelet packet, it gives us an opportunity in improving the frequency resolution. The higher you go, the better would be the frequency resolution. Okay. So this is the scaleogram of an ECG signal. So scalograms means CWT. A CWT this representation, it will look something like this. Now if you see, it is far superior than your STFT. Okay. Then wavelet based denoising, I'm not going into the details, so you can go for this removal of the different kinds of noises. So thank you. Do you have any questions?